Hello everyone. So we continue our course on digital logic circuit design. We start today a new chapter about memory and programmable logic. So mainly in this chapter we are going to cover different sections. We are going to explain the random access memory or RAM, as we all know. We are going to explain the memory decoding, how we can perform different operations based on the RAM memory. We are going to learn about read-only memory or ROM. We are going to learn about different techniques to implement combinational logic or design the ROM memory. Mainly we are going to cover the programmable logic array or PLA and the programmable array logic or BAL. So we start by explaining what do we mean by memory or what is a memory device. So the memory is a device which does exist in any electronic device we are having nowadays. It does exist in your cell phone, in your computer. Any digital device, we need to have a memory to store necessary information in this device. So the memory is a device in which we can store information and read this information or retrieve this information at later time. So mainly in the memory you can see different blocks or different locations. In each location we are going to store some amount of data or a number of bits in binary format, and these locations or these blocks we call it words. So we have here several words, and we can perform mainly two different operations or two main operations we can perform on the memory. We can either write in this memory, so we need to have some data available at the input lines and deliver this information or write this information in a desired memory location or in a desired memory place. And we can also perform read. So in the read operation, we are going to extract or retrieve the information previously written, previously saved in a certain location. We are going to read or retrieve this information for some output lines to be used with different devices. So mainly we can read or write. So in the write, we are going to input or enter some information in a desired memory location. In the read, we are going to extract this information to be used with another stage in the circuit or with another device. So mainly we have two different types of memory. We have RAM or random access memory, and we have ROM or read-only memory. So the RAM, as the title said, random access memory. So mainly we can read and write. So we can alter or change the information stored in this RAM at any time. For the ROM, we can only read the information previously stored. And mainly the ROM is used to store necessary information for the operation or the functioning of your device, start up, shut down for some specific operation related to the functioning of your device. We store the information in the ROM device. So mainly we can only read, we cannot change the information previously stored in the ROM. And ROM mainly is a programmable logic device, or what we call PLD, and the data is stored previously through a process called programming, or to control the input value for different gates, different AND and OR gates inside this ROM to store the information through the programming process. So now we focus more on the RAM or random access memory. So basically, why we call it random access memory? What does it mean, random access? So if you remember this device, this is a magnetic tapes. So as we all know, the time we take to access the information in this tape, or the information stored in this tape, the time we take to access information in different locations is different. You will take different time to access information at the beginning, or at the middle, or at the end of this tape. So this device is different than the RAM. For the RAM, actually the time we take, or the time taken to access randomly selected information in this memory is the same. So it's different than the magnetic tape, or the older magnetic tape. Here the time we take to access, to read or write the information at any location is always the same. So it's a random access. We will always take the same time to select any randomly word in this device. So, and each memory location contains a group of bits, and we call this word, we call this location a word. A word can contain as many bits as we like, and each 8 bits is called a byte, as you know. So if we have 8 bits in this word, this means we have 2 bytes stored in each word. So to control the memory or to perform different operations in the memory, we need some control lines. As I have said, we have different words or different locations inside this memory. So firstly, we need a way or a method to choose or select a specific word to either read or write in this word. So we need to have key address lines. So the key address lines is number of lines. The number of lines equal to k, so it contains k bits. And because we have k lines, so we can select up to 2 power k words. So we can have different locations. The number of locations are 2 power k. And then we need to control, we need to choose either to read or write. This is based on the 2 controls we have, read and write. One of them should be high at a time, so we can perform either read or write. We have some lines to enter the information or to store the information. It's in data input lines. And the number of these lines should equal to the width of the word. So we have here 2 power k up to 2 power k words, and each word contains n bits. N bits, this means we need to have the same number or the same number of lines, the same number n, to store the data in the selected word. We have also n data output lines. So here we can read, when we read the information stored in a specific address, we need to take this information through the same number of lines equal to the number of bits. So the number of bits is n. We need to have n data output lines. So let us see. Here, the memory, say we have the address line, say we have 10 address lines. So we have 10 bits in each address. 10 bits in each address, this means we can address or we can locate up to 2 power 10 locations, 2 power 10 words. So the number of words will be 1024, or 1 kilobit. 1 kilobit is 1024 or 2 power 10. So we have the number of bits is 10, and the number of locations is 2 power 10 or 1024. This 1k. And we can have as many bits as we need in each word. So if the read is 1, as you can see here, the read is high. This means the data already available at the input line. Sorry, if the read is 1, so the data stored in the address selected by the address we need will be read or will be available at the output line. This is when the read is high. When write is high, this means the data available at the input lines will be written or will be stored in the word selected previously by the address lines. So if we have a memory of size 64k times 10, this means we have 64k words. 64k means 2 power 16. So we should have 16 bits in the address line. So as k should be 16, this means we can address or we can select between 2 power 16 words or 64k kilo, and each word contains 10 bits. So each word contains 10 bits. This means we have 64 kilobits, for example. 640, because we have 64k times 10, so we have 640 kilobit. So let us see this example. So how many address lines and output lines are needed for a 4 mega times 12 RAM chip? So as you know, mega is 2 power 20. So it's not 10 power 6, and the kilo is not 10 power 3. It's different here. Mega means 2 power 20. So 4 mega means 2 power 2 times 1 mega, 2 power 20. This brings us to 2 power 22. So we should have 22 address lines, or k should be 22 address lines. This will enable us to select between 4 mega words. And each word contains 12 bits. This means we need 12 input lines, and the same number in the output lines, we need 12 output lines. So the number of the input and output lines are the same, equal to the width of the word or the number of bits contained in each word. So what should we do to write or to perform the write operation? So now we have some data at the input, and we need this data to be written in a selected word. So the first step is to apply a certain address lines. So we need to have some address and select a specific word based on this address. Then we need to write. So we need to have the data available in advance. So before activating the write control, we need to have the data available. The number of data, the data should be the same number of bits that can be contained in each word. Then we need to activate the write control. So we start by applying the address lines, then having the data available as input lines, then activate or enable the write control. This will allow us to store this data in the selected word by the address line. So we have 3 steps need to be performed in the write operation. To read certain data in a certain word, we need to perform only 2 steps. First, we need to apply the address lines. We need to have or to select certain word through the address line. Then we need to activate the read control. We need to have high as the read control. This will allow us to transfer the information stored in this address to the output lines. Now the output lines will contain the word selected by the address line. So now we can read the word or the selected word. As you can see, the read operation is non-destructive. This means the information stored in the selected word to be read are not going to be altered. We will still have the same information in the selected word. So after the read operation, we still have the same information in the selected word. In the write operation, write is a destructive operation. This means the input data will be written in a specific location, and the previously stored data in this location will be gone, will be destroyed, because we are going to write new information in this selected word. So the write is a destructive operation, the read is non-destructive operation. So instead of having 2 input for the read and write, we can have 1 control, 1 line for read and write. And if this line is 0, this means we are going to write the information in the selected word. If this control is high, this means we are going to read from this selected word. And if the memory enabled, so we need first to, in advance, we need to enable or disable this memory unit. So we have a memory enabled. If the memory enabled is 0, regardless of the condition of the read the write control, we are going to not perform any operation because the enable is 0. Once the enable is high, based on the read the write control, we can either write if the control is 0, read if the control is high. So we can use only 1 line to both operations, read and write. Now we need to design a circuit or decoder to switch between the read and write operations. So basically we have a binary cell. A binary cell is a digital circuit that can be stored to store single bit, either 0 or 1. And we need to have an input. This input will be written in this binary cell. The input could be 0 or 1. And we need to have an output. The output will receive the data to be read in this binary cell. So the output will be 0 or 1 based on the stored information in this binary cell. And we need to control switch between read and write. For doing anything, the select should be high. The select or the enable line for this binary cell should be high. If the select is 0, this means we cannot do any operation. We are not going to consider this binary cell for either read or write operation. If the select is 0, the select should be high so that we can either read or write information in this binary cell. This can be implemented using this simple circuit. Basically, we have SR latch, and this SR latch has 2 inputs, S and R, which are the output of the 2 AND gates. You have the control, you have single line for the read and write. So if this line is high, this means we have 0. This high will be inverted by the inverter. So we have 0 for the S, 0 for the R. The condition of this SR latch will be no change status. So whatever you have here at the output Q of this SR latch will continue to be the same. So no change operation because we have 0, 0. This means whatever stored previously in this SR latch will be available or will be transferred to the output line. Now this output, this AND gate, has 3 inputs. One input is high because we are performing the read operation. The other input is high from the select should be high. And then the data we have here from the SR latch, either 0 or 1, will be available as the output. So now we are reading the information stored in this SR latch. And at the same time, we are isolating the input line. So this input is really doesn't affect the circuit. You have 0, 0 here for the two end. So regardless of the input, we'll have 0, 0 as input of the SR latch. So basically, we are isolating the input from the whole circuit. So this is the read process. If we switch this line to be 0, so here we'll have 1, 1 instead of 0, 0, and whatever input here will be available as the S input of the SR latch. So say the input is high. So the input is high and the control is 0. This means we will have high here. We'll have 1, 0. 1, 0 in the SR latch will produce the set condition. So we'll have 1 here. So the input data now is available here or stored in this SR latch. So this is the write operation. We are writing the information at the input line in this SR latch. If the input is low, if the input is 0, so the SR and still we have 0 here. So and the input is 0, S will be 0, R will be 1. So we are storing this bit in the SR latch, and this bit will be read once the read control goes to the 1 states. So we can perform either read or write based on the condition of this line, of this control line. Read, we need to activate or enable the line. To write, we need to have this line equal to 0. So either we read the information stored in the SR latch and have this information available at the output line, or we write the information stored or write the information available at the input line in the SR latch to be read at later time once the control goes to the high condition. The whole circuit is available in this box, and we call it binary cell. The binary cell is a cell to store one bit, either 0 or 1, and we can either read or control, read or write the data or the single bit stored in this binary cell. Now we need to have a full-size RAM or practical RAM of many binary cells. So here we have 3 inputs: select, input, read, write, control, and 1 output. Select should be high all the time if we need to consider either read or write for this binary cell. In the design of memory or array logic, we need to have different symbols. So this is a conventional symbol we have been using so far. If we have OR, AND with multiple input, so we have this multiple input as horizontal lines. Here, to make the design easier, when you do it by hand manually on paper, we need to have, instead of having 4 horizontal lines, we'll have 4 vertical lines. Still, this OR is accepting the 4 vertical lines. So basically, imagine that these 4 lines are horizontal line getting inside this OR. And the horizontal line is indication that these lines are getting in the OR. So the 2 symbols are the same, but the way we represent it or draw it on paper is different. In this chapter, in designing the memory or array logic, we need to have vertical lines as the input of this OR gate. This will make things much easier. You can do this with AND or both are the same concept. So here we have 2 things actually. We have a decoder, and this decoder is n by 2 power n or 2 by 4. So we have 2 address lines, 2 input lines, and 4 output. And the single output will be high at a time. The others will be 0 based on the address line or the 2 lines we have at the input of this decoder. And each output line from the decoder is connected to 4 binary cells or 4 bits. So basically we have 4 locations, 4 words times 4 bit. So we have 4 by 4 RAM. 4 by 4 RAM or 16-bit RAM. Basically, first thing we need to enable, so in each binary cell we have the decoding circuit we have just explained. So we have read-write control. This will control the operation either read or write. Select should be high. So the select is this vertical line getting in. So this select line should be high. Then we need to control the circuit using read or write, and either will store the information in the write operation or take the information out in the read operation. First off, the enable for this decoder should be high, so that we will enable the whole circuit or the whole design. Then, based on the address line, so if the address line is 0, 0, this means one output of these 4 output lines will be high at a time. Because we have 0, 0, so the first line or the first output number 0 will be high, others will be 0. This means only one row is enabled, one row is activated, which is the first row or the first 4 bits. So the other rows are not considered as if they are not here. Now we have selected this row or these 4 cells. We need now either to read or write. So if we have this control to be 0, this means we are writing information in this binary cell. So whatever you have here, as input data, we have 4 lines, 1, 2, 3, 4. This input data will be stored in the binary cell, as we have just explained in the memory decoding circuit. So when the read write is 0, we are writing the information. So the information we have here available will be stored inside each of these 4 binary cells. If the control is high, so this read operation, so whatever you have stored previously in this binary cell will be available at these OR gates. As you can see, we have used the new symbol of this OR gate. So each OR gate actually is receiving 4 bits, 4 input. One input from this binary cell, another input from this binary cell, another input from this binary cell, another input from this binary cell. So basically we are receiving 4 inputs for each OR, and only one input will be activated, will be enabled at a time, which is enabled by the decoder output. So the decoder will enable one row, and this row or this binary cell will be either written in or read from by controlling the read write, either 1 or 0. So if the control is high, if this control is high, this means the information which was previously stored in this binary cell will be available at the input of each OR gate. So if we have 1 here, so the output of this OR will be 1. If we have 0, the output of the corresponding OR will be 0. So the information stored will be read and will be available at the output lines. So basically, if you need to have, say, 2 power k or 2 power n words, you need to have a decoder with the same number of output. So the number of input will be n 2 power n output of this decoder. This is the basic decoder we have studied before in chapter 4. So we have 3 by 8 decoder, we have 3 input lines and 8 AND gates, and each AND gate is producing 1 main term, as you know from chapter 4. We have another way of decoding the address, of choosing a certain word. To say we need to design a RAM with 1 power k words, so the number of words is 2 power 10, 1024. This means we need a decoder with the same number of output. We need a decoder with 2 power 10 output lines or 1024 output lines. This means the decoder should have 10 input lines. This is a big decoder. If we don't have this decoder, we can have 2 decoders, each decoder with input of only 5 lines. So instead of having 10 input lines for the decoder, we can, the original decoder, the big decoder, should have 1024, the same number of output, AND gates, which is large number of AND gates. If we don't have that large decoder, we can have 2 smaller ones with the input lines of 5 lines. The output is 2 power 5, 32. This means each decoder will contain only 32 bits. The 2 decoders both contain 64 AND gates, which is much lower than the previous decoder, the bigger decoder. We need only 64 AND gates. But how are we going to use this decoder to locate, to address 1024 bits, 1024 words? Say the address line, the given address line is 10 bits, 011001010. So we are going to treat each 5 bits separately. The first 5 bits is X 01100. The other 5 bits is Y 10100. So one decoder will be used for the first 5 bits of the address. So this is the address 10 bits. One decoder will be used for as X input. The other decoder will be used for the other 5 bits as Y input. This X input, in this case, X is 12. So we are going to enable this line 12, and when Y is 10100, which is 20, so we are going to enable this line. So basically, we are activating line 12 from this decoder, and line 20 from this decoder. So the intersection will be the selected word, the selected location, which has the address of 10 bits. So instead of using one big decoder, we can use two smaller decoders with actually 50% of the input lines compared with the bigger decoder, and we call this mechanism, this method, coincident decoding. Coincident decoding because we are going to activate one horizontal line defined by the first 5 bits of the address in this case, and this line will have an intersection with another vertical line enabled by this decoder, which has input as the other 5 bits of this address. So this intersection point will be the selected word, and now we can just save the bigger decoder and just use two smaller decoders. So that's it for today.